Hello and welcome back to Data Office Hours. My name is Frank Lavinia. I'm the Global Go-to-Market Lead for Data Services here at Red Hat. And with me today, I have a very special guest, Akanksha Dugal, who works out of the Office of the CTO, and she's doing some amazing things on homomorphic encryption. So stay tuned and check it out. All right, Akanksha, welcome to Data Office Hours. What do you got to show us today? I hear you got some cool stuff.
Hey, Frank, how's it going? Thank you for having me on your show. Today, I'm going to be talking about homomorphic encryption. So should I go ahead and share my screen?
Well, first, explain what, because when you and I were talking, what you described as homomorphic encryption sounded impossible. I've heard you present this, and I remember saying, like, that's not possible. So tell us a little bit about it and why it's important.
So to give you an introduction, most of us have like mobile phones, internet access, and we're almost on our machines all the time during the day. And oftentimes, these websites are collecting our data, sometimes with our consent, sometimes without our consent. And most of us are oftentimes worried, like where is this data being used? Are they collecting some personal information? And at the same time, all of us want good Netflix, YouTube, TikTok recommendations. So homomorphic encryption is a concept that allows you to perform any sort of operations on the data that you have, at the same time ensuring that your information is private and encrypted and still getting the best inferences out of it. So that's what is the coolest part about homomorphic encryption, and I'm here to talk all about it.
Awesome. Yeah. So I think one of the things is, they're capturing the data, but you want to make sure that it's safe where it's stored. And because you don't want your private data to be in a CSV somewhere in the cloud.
Right.
Is this different than encryption at rest? And how so?
Yes. So I'll give you an example again. So if you are somebody who has an amazing machine learning model that I want to use on my data, but I want to ensure that you don't have any idea what my data is about and what kind of information lies inside my data. Instead of sharing my data right away with you, what I'm going to do is generate a pair of keys which will securely encrypt my data, and I will be the only owner of the keys that can encrypt and decrypt this data. And I encrypt this data and send it over, and your model is going to just see the encrypted side of it, make inferences out of it, and even you would not know what answers this model is going to give back. And you send me the encrypted version of the answer, and only I can encrypt it back. So this is how this chain usually works. And the person who's the model owner and the AI provider would never know what the data was like.
Wow. Like I said, it sounds impossible. So let's see the slides in the demo, because this is straight up science fiction.
Awesome. To welcome everyone to my presentation, I'm going to be talking about homomorphic encryption in the open source world. As I mentioned earlier, what is homomorphic encryption? It comes into picture when lots and lots of data, private user data, is being collected, and homomorphic encryption can allow us to make inferences, make the best use of the data, but ensuring that the customer's data is private at all points. So before diving deep, I'll take a quick moment to introduce myself. My name is Akanksha Dugal. I'm a senior data scientist in the emerging technologies team in the office of the CTO at Red Hat. I live in Boston, and I've been in this role for 3 years now. Here are my creds. If you want to reach out to me, talk to me about homomorphic encryption, have any cool ideas to bounce on, I'd be happy to do that. So let's get into homomorphic encryption. So if I believe most of us know what encryption is, but still I'd like to take a moment to explain what that is. It's a way of scrambling your data in a way that only authorized parties could understand certain types of information. In technical terms, it's the process of converting human readable plain text to incomprehensible text, which is also known as ciphertext. And homomorphic encryption is a kind of encryption that allows computation on this encrypted data. In short, it ensures that performing operations on encrypted data and decrypting the result is equivalent to performing analogous operations without any encryption. So, as most of the companies continue to develop machine learning models for different tasks, and sometimes these models are a key asset and cannot be shared publicly for different reasons. And on the other end, users also have private data that they don't want these models to see. So, homomorphic encryption bridges that gap and lets the user encrypt their data in a way that it can be computed on as if we are computing on a plain data. And thus, they only send the encrypted data to the model owner, who can evaluate the model on this encrypted data and return back an encrypted result to the user, who is the only person who can decrypt this back. Talking about what kind of applications homomorphic encryption can have, it has numerous applications ranging from healthcare to smart electric grids, from education to machine learning as a service. Basically, all sectors where input privacy is paramount, and making use of this data is usually already very complex due to regulations or the significance of the data and the security concerns associated with it. One of the most important use cases of homomorphic encryption is in the healthcare industry, where precision medicine would require intensive computation on highly identifiable data. But patients are concerned about the privacy and the agency against breaches. So the agencies and hospitals must ensure compliance with the relevant laws like HIPAA. And pharmaceutical companies are also worried about protecting their IP. And these trade offs and regulations come with disastrous outcomes for both the organizations and the patients. So, homomorphic encryption plays a very vital role here in providing a novel solution to some of these trade offs at a cost that is minimal compared to the disastrous outcomes that could come with HIPAA. Talking about where homomorphic encryption lies in the open source world, so both open source and homomorphic encryption promote transparency, ensuring of algorithms, implementations, and also enhancing security. It encourages a collaborative environment for researchers and developers, and also ensuring the privacy of their data. So important use cases lie in like protecting sensitive information that is related to the contributors and the data of the open source communities. Also enabling secure collaboration, because oftentimes competitive companies are collaborating on an open source project and there are multiple parties that are involved here. And homomorphic encryption is also famously known as multi-party sharing. So it allows multiple parties to use their individual data for the same model and then finally decrypt back the results without technically knowing the initial data set, which was encrypted by two different parties. Homomorphic encryption also allows you to protect the intellectual property because open source projects rely mainly on open collaboration. So it's really important to protect the intellectual property, such as the code and the algorithms associated. Also ensuring data privacy wherever data is involved in these projects, ensuring that this data is encrypted at all points and still getting used for making the best computations. And oftentimes there's also voting processes associated with these communities. We can also try to secure this process by ensuring that homomorphic encryption is in the picture. So these are a few applications that homomorphic encryption would have in the open source contributing world. Coming to the advantages and the disadvantages of homomorphic encryption, we know every coin has two sides, so nothing is perfect. So let's go ahead with the advantages first. We can perform inferences on encrypted data, as I mentioned, in a way that both parties don't share their data amongst each other, and it does not require any sort of interaction between the data and the model owners. So it's pretty seamless the way the computation happens. It also allows you to outsource the data storage and processing because you are not technically involved in the storage processes. as you mentioned, Frank, that we don't have to be worried about our data lying somewhere in some S3 bucket. So these are a couple of advantages. But when you talk about disadvantages, homomorphic encryption is computationally expensive, and most of these workloads are not defined in homomorphic encryption friendly way. So computation cost is one of the biggest disadvantages which homomorphic encryption has these days. But I hope in no time we'll be able to resolve that issue as well. Um, Talking about other restrictions, there are restrictions to certain kinds of calculations. So division and comparison of values can be super costly. Um, it's almost really hard to compute division in homomorphic encryption, especially when you talk about machine learning. Algorithms, it's usually math intensive. And when you talk about homomorphic encryption, it doesn't even allow you to perform basic calculation like a division calculation. And data filtering, which is also a very common thing when you're preparing your data before you start to perform data science calculations. So the first thing you do is get your data, clean it up, filter out things that are not important, and see what you want to keep before you move forward with the intensive calculations. So data filtering is also not possible when it comes to homomorphic encryption because everything's encrypted. You would not know what to remove. So these are a couple disadvantages. But all in all, I think advantages are winning over disadvantages. Um, so let's go ahead and go over like the history of homomorphic encryption and what are the types of homomorphic encryption, how it has evolved over time. Um, Starting with the first one, which is the partial homomorphic encryption. The scheme can evaluate any circuit that is composed of a single type of gate, uh, addition or multiplication, but never both. It does not restrict neither the size nor the depth of the circuit. And this type is well suited for applications that only need to perform either addition or multiplication on encrypted data. The RSA crypto system, which is like one of the first, uh, the rule of thumb for encryption, is an example of PHE, and it also allows an unbounded number of modular multiplications. Um, Paleo crypto system is another example for the partial homomorphic encryption. With time, we've come forward. There's another type of homomorphic encryption, which is called somewhat HE, which is also called SHE. This type of scheme can evaluate circuits that are composed of addition and multiplication gates. But there's a restriction on the depth of calculation you can perform here. It's usually helpful when you want to evaluate a low degree of polynomial up to some level. And sometimes we do need to evaluate circuits with an arbitrary depth. So SHE is not the best here. And then comes fully homomorphic encryption, which is the HE that we are following these days. As the name suggests, you can literally do anything under FHE. So this is composed with circuits that are composed of both multiplication and addition. And in contrast to SHE, FHE has unlimited circuit depths and it makes it suitable for deep learning applications. And all FHE schemes use a specific type of post-quantum cryptography called the lattice cryptography. And most of the fully homomorphic encryption libraries would require deep expertise of the underlying cryptographic schemes to be both used correctly and efficiently. And CKKS and BGB schemes are the types of schemes that fall under fully homomorphic encryption. I would not go into a lot of technical depth here because these days we have so many libraries that we've also performed a comparison study on. So we would not want to know the depth of the calculations involved. We can rather just directly start to use it. So as a part
Yeah,
of
I would say like encryption and some of the math that goes in here, it gets
Mhm.
very deep very, very quickly.
Yeah,
And
yeah.
like I'm only following along because a long time ago, I worked on a steganographic detection system, RFP. So
Mhm.
that's where I wish if I had known I'd use all this math, I would have paid a lot more attention as a kid in math class. But I had to relearn it when I did this. So like that, I mean, otherwise I'd be completely lost. So one thing you dropped one line in there, which I know is going to come up. So that so these models,
Mhm.
well, a couple of things, right? One, it is computationally expensive, but you can enable
Yeah,
things that are supposed to be impossible, right? So
right.
sometimes doing the impossible does require a little bit of extra, muscle, whether
Yep.
that be computational muscle or otherwise. The other thing is, you said that these, did you say all these algorithms or most of these algorithms are quantum safe?
I meant that for the fully homomorphic
Fully
encryption.
homo. Okay, cool. All
Yeah.
right. So for those wondering, what the heck is Frank saying? Quantum safe encryption is the type of encryption that we believe will be resistant to innovations in quantum computing, which is a whole other thing I can geek out, but not now because I interrupted your flow. But please continue. Sorry about that. I want to make sure we didn't lose the audience.
Yeah, you can definitely stop me whenever you like. I'm happy to answer all the questions because, like, we did spend like a lot of time figuring these things out ourselves. Because myself, I am not an encryption expert. I'm also a data scientist. So we just try to bridge that gap between data science and encryption and try to come up with something that can support data scientists. So, coming to that, we performed a comparison study. So, the idea behind this initiative was to do a proof of concept and try to see what lies in the market for us, like specifically in the open source world. What is there that we can use to ensure that there's privacy at all points while we are applying our machine learning algorithms? So, we started out the research, and by the first Google search, we would know that there's a clear winner in the market. It's called the Microsoft Seal. It is written in modern standard C++, super easy to compile and run in many different environments. But as I said, we wanted to align this with our work, which is in the data science world. And most of the code that we at Red Hat write is in Python. And if we were to integrate this, we would definitely want to look for something which is written in Python language so that we can directly perform an import in our notebooks and just try to encrypt the data right away. So we try to look for open source and Python-based libraries. So the first thing that we stumbled upon was the Python failure library. Super easy to use. It is based on the Palia crypto system that was invented by Pascal Palia in 1999. It is the partial homomorphic encryption scheme, and it only allows you to perform addition on two ciphertexts, multiplication, but only on one ciphertext and one plain text. And this implementation is available in the Python Palia library, which is just a pip install in your notebook, which I'll demo quickly after this. And I would say that this is not super awesome in terms of doing a homomorphic encryption application. But if you're getting started with encryption and performing calculations on that, I think this is the library that you must start with because this clears up a lot of basic concepts. Um, then we also found another library which is called PySeal. It is now an archive, but this is a wrapper function of the Microsoft Seal library. It was super great, but it required a lot of building and like a lot of config files, and you have to like do it something inside a folder. A lot of dependencies, which I don't think data scientists would like when they are working on their code. So we thought, let's dig deeper. We found PyFHE, which was developed by some folks at MIT a couple of years ago. It is also fully homomorphic encryption library, and it includes all the schemes, as I mentioned, the SHE and FHE schemes, both BFE, CKKS, and all sorts of calculations that you would want to perform. But we thought that this lacks a little bit of documentation. It's good to use, but not super user friendly. So we are just still digging deep here to find that one library that works the best for our work. We found PyFell, which is also an open source library. It has numerous applications, numerous calculations that you can perform here. And this is great to use. And we also found another better library, which I'm going to explain why we think this is the best library according to us. So TenSeal is developed by OpenMinded. This is an open source library. It's built on top of Microsoft Seal. It provides us to use very easily using a Python library. As I mentioned, we are using looking for that pip install that can seamlessly integrate with our workflows. And this has excellent features that enable encryption and decryption of vectors, of integers using BFV and real numbers using CKKS, and more operations like element-wise addition, subtraction, multiplication of encrypted and encrypted vectors, dot product, vector matrix multiplication, and all of this with no dependencies and just one pip install, and you can just go ahead and start using it. And besides basic operations on encrypted data, it has more advanced usage for machine learning applications like logistic regression and encrypted convolution as well. And it's on the top of that, it's all open source, super easy to use, very well documented. So we did a proof of concept using this library to see how well this actually works, which I will quickly go ahead and start to demo.
Yes, please. I love to see
Awesome.
this in action. And
Yeah.
I think you said something that I think is important to point out too. Obviously, it helps if you know something about encryption, but if you are a data scientist and the math doesn't scare you, you could probably just use these libraries. And as long as you have a
Right.
reasonable proficiency in what's going on, because that's the danger with encryption, as I understand it, is that one break in the chain of security, the whole thing is lost, right?
Yeah.
So just make sure before you do this, make sure you have a full understanding of where things are and where they end. Just putting a safety out there for the kids
Yeah.
who want to try this at home. So sorry, I cut you off again.
Yeah, awesome. I think I'm gonna go share my screen. So this is the home repository for all the work that we've put together so far. We have put together the documentation of how we've come up with the proof of concept, how many papers we've read, and how much research we've done behind this. And we've also put together a couple Jupyter notebooks. So for those who don't know, Jupyter notebooks are fancy way of using Python scripts. We just put everything in a cellular format, and we don't have to run the entire script, and we can just directly see our results in the notebook while we are performing our calculations. So it also allows you to put documentation like Markdown together with the Python code. So we really like to present our work in this way. So now we can go ahead and talk about the Paleo crypto system first. As I said, this is the library that you're looking for if you're getting started with homomorphic encryption. Um, Super easy to start with. Let's skip this part and move towards the example. As I said, one pip install and you are all set to get started. You take two numbers. We've taken 30 and 40 here. Two lines of code to just generate the public and private key pair here. And it's as simple as going to encrypt these numbers. So we're gonna just encrypt cipher num1, cipher num2, use the key, encrypt number 1, and encrypt number 2. So no math involved, and you can just directly encrypt your numbers here. And then you can also decrypt this result by doing dot decrypt. What we're going to do here is add these two encrypted numbers together and store it in the form of result. And we can also decrypt it back. On printing the result, we see that it's absolutely correct. The answer was 70 when we try to add these two encrypted numbers. So having said that, this encryption works fine. As I said, this is back in the 90s. Getting the right answer on encrypted numbers was also a big thing back then. Then we also try to perform scalar, and then also we get the correct answer. Then we try to see how long is it taking. Like, I know we are getting the right answer, but how long is it taking? So we saw that homomorphic encryption took 92.8 microseconds, whereas the vector addition took 102 nanoseconds. So if we were to see how fast is this, we can say that the vector addition, which is the normal form of addition, was 1258 times faster than homomorphic encryption. And this is just for basic calculation like 30 plus 40, which usually people perform in a second in their head. And that's how slow homomorphic addition is in compared to the normal addition. So that's
So
that.
it's a
But
lot. When you said it was
yeah,
computationally expensive, you weren't kidding.
yeah,
It wasn't like, oh, it's 50% more, or it's
yeah,
100% more, 200%.
yeah,
I mean, it's a lot. Okay, that's good to
yeah.
know.
But But yeah, this is also, I'm going to come to that part, but this is
Okay.
the one that we used in the 90s. So I'm going to slowly build up to where we are today. Um, so another limitation that PHE had was that you cannot multiply two ciphertexts together. So when I tried to do that, I got a very funny error which said, good luck with that. So very cool library to start learning and trying it out. So this is the failure library that is available, and you can just try it out. And slowly, there were many libraries that we checked out. There's PyFell, there's Tensile, but I think I'm gonna go over Tensile, which is the library that I mentioned, was the best according to data scientist need. Um, so we use a lot of vectors when it comes to performing calculations. Like oftentimes data is not, as simple as two numbers. It's often an array or a data frame kind of thing where you would want to apply your algorithms to. So Tensile allows you to perform calculations on vectors, so which was the correct fit for data scientists. So I think this is the best library in my opinion. So for integer calculation, the scheme called BFE is used, and for real numbers, CKKS is used because you can use decimals and you can use the approximation of these numbers to perform calculations. So I will use the same example we used for the Paleo library and try to do a comparison here to see how far we've come in these many years. So again, as I said, the ease of use, import Tensile as TS, and it's as simple as that. You just create a context and try to encrypt your numbers. So it's literally the same thing. You take your vector, code is slightly different. You do ts.bfe vector, put your context in plain vector, and you'd be able to encrypt your vector right away. So not too hard. The documentation is great if you're trying to follow along. And then we try to do a calculation between cipher to plain text and try to decrypt the result. That was also super seamless. But I think I'm going to jump to the part where we try to calculate the time that it takes to perform these calculations. So again, we have two vectors. Random numbers here. We try to encrypt them and try to see how long it takes to perform the addition. We see that when we're trying to do homomorphic addition, it takes 24.9 microseconds, and vector addition took 1.71 microseconds. So if you were to compare the time now, the vector addition is 14.59 times faster than homomorphic encryption. So this is where we've come today. This is the present world scenario. So and mind you, these are not just two numbers that we are adding. This is an array that we are trying to perform computation on. So definitely we've come very far from where we started, but still there's little room. When it comes to performing intense calculations, it'll take much more longer. But if it comes to basic addition of vectors, I think 15 times is not too bad, in my opinion. I think we've come pretty far, but the day is not far where it's going to be much faster than this. And for subtraction, it's almost the same. For multiplication, it takes slightly more longer. So vector multiplication is often more intensive because you have to multiply element by element. It's 3,000 times faster for the normal multiplication. So that's the tricky part. If I go to more intense calculation with real numbers in CKKS, if we were to do negation, it's 42 times faster for the normal one. If you were to do exponents and powers, it's 3,435 times faster. Dot product is also around 5,000, close to 5,000 times. Matrix multiplication is also 3,600 times. So approximately, this is much more computationally expensive, but this is still very fast, and more detailed calculations can be performed using these libraries. So that's how far we've come. And I think I'm going to go ahead and deep dive into the proof of concept that we did, which is the real world application of how we put homomorphic encryption to use in the data science world. So if and when we get started with data science, like few of the early algorithms that we learn is logistic regression. So I try to do logistic regression in the simple way, which is super simple these days, one line of code and you're done. And I also try to perform it on the encrypted data set and train it on an encrypted data set and test it on an encrypted data set. So that's what I'm going to show here. So downloaded a normal data set from Cable. This is heart disease data set, and I'm trying to make a prediction on how you can reduce the risk using the past data that is available. And once I get the data, sorry, one second. Once I get the data, I try to deep dive into the data and I try to train a logistic regression model using the plain text data. As I said, it's been really easy to do data science calculations these days. If you know what's going behind the picture, you just do an import of this sklearn model and just go ahead and create a classifier, fit your training and training data over here and make a prediction on it. And you can get a fancy report over here, which tells you about your precision, accuracy, recall value, and et cetera, et cetera. So here we can see that this barely took a second. The moment you run the cell, it prints a result right there. The accuracy we got was around 83.6%, which is pretty good for linear logistic regression model. And now I'm going to just skip over a couple. So we did a lot of experimentation over here. I'm going to skip that part and go directly towards the part where we train our data on, train our model on an encrypted data set. So we take the same data set that we have, we encrypt it using this class that was being made available by Tensile itself. So you encrypt your data set and try to do the same logistic regression. So we try to train this model, and they say that encryption of the training set took 66 seconds, which is not too bad. But this is also a small data set that we are looking at. And once we've done this calculation, we try to see how accurate our results are. So we see our accuracy is 0.57, which is great considering the logistic regression was done on an encrypted data set. And when we try to see the accuracy on the tested data set, we saw that we were getting a better accuracy even when we are training on the encrypted data. So we try to do it over multiple epochs and try to improve the accuracy every time we're training the model on the encrypted data. And we see that this is foolproof, and you can literally perform logistic regression the same way you can perform it on the plain data and the encrypted data. It's literally the same thing, and you oftentimes might get better accuracies or something. But this is, again, a small data set that we're looking at. There are like 4,000 rows in this data set, but still it took a while. So I would say the average time per epoch was 350. So 350 seconds, which is not too bad. But in the real world, the data is not this small. It's millions and millions of rows. So definitely this is a limitation, but still I think we are on the right track in terms of right accuracy and the ease of calculations that we can perform. There's also CNN, which is the convoluted neural networks. And you can also try to perform any sort of calculations using that. You can detect images, the MNIST data set, which allows you to identify numbers from 0 to 9. That is also possible using homomorphic encryption at this point. So these are like two basic proof of concepts that are ready to use in terms of homomorphic encryption. And that's that. This is the demo that I had. If you have any questions, I'm happy to answer that.
Well, it's very cool. I mean, it's you weren't kidding when you said it was more computationally expensive, right? Like it can be, but I mean, for some scenarios where, it's a good thing you use medical data, right? Like there might be other things in there that you just couldn't do this any other way, right? Or for reasons many and for reasons large and small, right? Like so, I think that it becomes a cost of doing business, I suppose, in certain emerging spaces would be one way to look at it. The other thing I would add would be the question I had for you was, I just so we're clear. So say I had a model that predicts whether somebody has diabetes, right?
Okay.
You send me your data set encrypted. I can't see anything in there. Do I, as the model owner, get to see the answer, or is that also encrypted? I think it is, but I want to be clear.
That is encrypted.
Okay,
so the key lies with the client. So you at no point would get to see the data.
Okay. All right, that makes sense. So that way it's not a situation where, hey, I know you sent me data and I know that 10% of the people that you sent me have diabetes, right? Like it's not like that. I won't have any idea.
Yeah.
Yeah, that's interesting. So I think it's important because I think as our models, as the world becomes more data driven and we have more privacy awareness, I would say, and regulations are
Yeah.
coming in, this is going to enable a whole new class of models to be created and with data sharing in a way I think makes people comfortable. Now, I know you're not a lawyer. You probably never even played one on TV, but I mean, is this type of schema, acceptable to something like HIPAA or maybe even GDPR? Like, is that something that and as much as you can answer because you're not a lawyer, but like, I mean,
Yeah.
has this gotten the green light from something like HIPAA?
Yes, for sure. So that's where the biggest use case of homomorphic encryption lies in, because the pharma industry, the medical industry, they have the most confidential data of their patients. And with HIPAA in picture, it's oftentimes difficult to comply with the rules. So I think homomorphic encryption is one thing that will definitely protect you, shield you from HIPAA laws at all points. And I know a couple of companies who've been using homomorphic encryption. uh, the other thing is the federated learning models that you can use. You can encrypt your models and send it to places where the data cannot be sent over because of the volume of the data. Because, as I said, there's computational limits. So I know like a couple companies have been doing that lately. They've been encrypting the model and sending it over to the pharma companies who can use the model but not know what's inside it. It's like a black box to them. And they can make computations out of it, and it's as simple as that. But if foolproof homomorphic encryption would be when you encrypt your data and your data doesn't lie anywhere, even if it's secured in a remote location. I think it's still not secure. It has uh, a room to escape. But when it comes to homomorphic encryption, where you encrypt it right away, I think that's the way to go about things and ensuring your data is private at all points.
Interesting. Well, this has been an awesome office hours. Where can folks find out more? We'll make sure, obviously, there's the repo, and we'll make sure folks can get. I'll put that in the link in the show notes. And thanks for
Yeah.
joining. Anything else you'd like to add?
I think that's all for now. We are constantly working on getting FPGAs, which is the accelerators, added to this workflow. And we're constantly working on that with a team so that we can accelerate our processes and ensure that same calculation is performed in a much faster fashion, less memory is consumed, so that we can actually start to apply this to the real world. So we are actively working on that. Hopefully, we have an update. Couple months or couple years maybe, but we are constantly working on that, so stay tuned for that.
Awesome. I thank you very much for joining, and see you next time.